Okay, this is the start of 9.2 in 20-1 math, where we talk about quadratic inequalities. Not very different than linear inequalities. We're going to actually solve them very, very similarly. One thing that I'd like to really encourage you to see is that when we do look at maybe ax squared plus bx plus c is less than 0, one thing that can really help is identifying that if we were to graph y equals ax squared plus bx plus c, is equal to y, that's less than 0 when the function is negative. And when we talk about the value of the function, what we are talking about is the y value on that graph. So one of the best ways of graphing these or solving these quadratic inequalities is actually to graph the quadratic inequalities. And I'll talk about, there is another technique as well, but the one that we're going to focus on the most is certainly graphing these. It's part of the reason why we spend so much time talking about graphing quadratics in Math 20. Quadratic inequalities show up a ton in other math courses as well. So please don't think that this is just something we force you guys to do. Now, when we want to solve an inequality like x squared minus 2x minus 3, I'm just going to write that really what we could look at is x squared minus 2x minus 3 is less than y. And we just have to identify, okay, when we talk about this being y, less than or equal to y, I should say, sorry. As long as y is 0 or less, that quadratic inequality is solved. And I like to just talk about that if we look at a number line, what I'm drawing right here, that red line is when y is greater than or equal to 0. And then I'll do the open dot just so we can see it. That line is when y is less than 0. Now, the reason why that's so important is when we talk about y, we're talking about that quadratic function. So what I'm going to do for this question is I'm going to graph this quadratic. And the easiest way I think of doing that is really kind of twofold. Number one is that we have a positive a value. So I know that my quadratic opens up. And then really, number one, that's pretty arbitrary. Number two, I'm actually going to factor it as well. So if I factor that, I get x minus 3 times x plus 1. Now, really importantly, that means that my x-intercepts are going to occur when x is equal to 3 and when x is equal to negative 1. And the reason why that's so beneficial is, at the very least, we can get a pretty, good look or reasonable look at what this graph looks like. A lot of students struggle with the idea that we don't care what the vertex is. The vertex really doesn't add anything to the solution to this problem. We want to find out when this function is above the x-axis or below the x-axis, because when it's above the x-axis, it's greater than or equal to 0. When it's below the x-axis, it's less than 0 or less than or equal to 0, which it will be in this question. Now, knowing the x-intercepts allows me to plot them. So there's x equals negative 1. There's x equals 3. I'm just going to put those values maybe a little bit to their left there. And the other thing that we should be able to identify pretty reasonably is that this has a y-intercept at negative 3. Right? Take a close look at that function and make sure that you can identify where that y-intercept is. It is the constant value in our quadratic. Now, with our knowledge from chapter 3, we could then actually graph a pretty reasonable, I would argue, graph where the quadratic is going to open up. I don't care where the vertex is. I know it's below the y or x-axis. That doesn't particularly matter. Now, the reason that this is beneficial is keep in mind that this red function is x squared minus 2x minus 3. So when we talk about solving this, and I'm actually going to put both solutions on here. If I was to solve x squared minus 2x minus 3 is less than or equal to 0, now that's the question. This function is less than or equal to 0 when x is 1 all the way to when x is 3. And, I'm putting that on the x-axis, but really what I'm, identifying here is when this red parabola that I'm kind of wiggling there is underneath the x-axis. Because when my parabola is underneath the x-axis, it's less than 0. When it's above the x-axis, it's greater than 0. And when my parabola is on the x-axis, namely the x-intercepts, it's equal to 0. So the solution to what I put in blue here would be, okay, x has to be greater than or equal to negative 1 and less than or equal to positive 3. And that's an oversight on my part. That should certainly be a negative 1. Sorry about that. All right, I do want to put kind of the other side that this question could ask. What if it asked, when is x squared minus 2x minus 3 greater than 0? And, I'm trying to color code this so we can see them all together. This parabola is greater than 0. Anything less than negative 1, but not equal to negative 1, it's 0 at negative 1. And anything greater than positive 3. Again, not at positive 3 because it's 0 at positive 3. So if I was solving that green inequality, I could say that happens when x is greater than positive 3 or when x is less than -1. Now, I know that wasn't part of the question, but I think looking at those two things together can really, really help. When the function is above the x-axis, it's positive. When it's below the x-axis, it's negative. But we often, recognize positive as something greater than 0 and negative as something less than 0. All right, we're going to keep going with this kind of graphical technique because it's the one that I find kind of nearest and dearest to my heart. There is another technique called a sign chart, but we typically don't start doing that until calculus.